Hello, good morning, good evening, good afternoon, everybody, wherever we might be. It is my great pleasure to host PAWEL SARKOWICZ from Canada, from Ontario, right? And he will tell us about homology and universal covering groups of unitary groups. It's all yours. Take it away.
All right. Thanks very much for the introduction. Thanks for having me. Yeah, I'll talk about homology, universal covering groups. So here's a brief outline. We're going to talk about group homology, mainly these first two homology groups. And by group homology, I mean homology of groups, homology of a discrete group. So I'll say what this is. And the first two ones are of interest. And then second part of the talk, we'll talk about determinants to look at groups associated to C-star algebras, like unitary groups and general linear groups. And we'll look at their first or second homology groups. And the third part of the talk, we'll talk about the universal covering groups, which are from algebraic topology. And there's this question of whether or not some universal covering group is perfect, and I'll give an answer. And we'll talk about what all the universal covering groups of von Neumann algebras are, or of unitary groups of von Neumann algebras are. Yeah, let's get started. Usually A will be a C-star algebra, just to lay down some foundations. M will be a von Neumann algebra. G will be a group, and it'll be discrete. Okay, so to a group G, we can actually associate some homology groups. So these are some weird abelian group that kind of measures something. It comes from algebraic topology as well, and in that setting, it measures holes in your space. But this is the Eilenberg-MacLane homology. So how do we come up with this thing? How do we?
Sorry, we cannot see
Hello?
what you're writing. The Eilenberg.
Oh, MacLane. Sorry, yeah, my.
No, but
I'll try to be nice.
Oh, okay. Is
that okay?
Yeah.
Okay, I'll try to be as neat as possible.
Sorry, what do you mean by Eilenberg-MacLane? Those are abstract axioms, yes? Not the specific type
Well,
of...
okay, they're homology groups.
No,
So
but what I wanted to say is that there are Eilenberg-MacLane axioms for a generalized theory of homology, yes? Or you mean something
yeah,
else?
but
Sorry,
these are
I
often
understand.
like with the integer coefficients, this is often called the Eilenberg-MacLane homology group.
Yeah, but do you mean just, for example, one particular construction of a group homology or cohomology is the homology or cohomology of a classifying space, yes, of this group?
Yeah, exactly, yeah.
Okay,
Yeah.
I see.
Yeah. So exactly, to G we associate a classifying space. And this is a space for a discrete group, so that the fundamental group is G, and every other homotopy group is 0. And this is unique up to
No, but
homotopy.
no. Probably you're speaking now about the Eilenberg-MacLane spectrum, but not BG.
Yeah, well, the
I'm a
classifying
bit
space, and
confused.
then you take the homology of the classifying space, and then this is the homology of the group.
Yes, but
So
this
HN, this is the topology of BG with integer coefficients. Yeah.
Yes, for this, I'm fine with this, but with this nth homotopy group being G only in one entry is
For discrete group G.
for n equal to 1. Okay.
Yeah. N equals
Okay.
1. Yeah.
Okay, I
Yeah.
confused it with the so-called Eilenberg-MacLane spectrum, which is something
No. It's just
different.
these are called the Eilenberg-MacLane homology groups, and they just come from the homology groups of the classifying space of the group.
Okay. Sorry for that.
This is from algebraic topology, so this measures n-dimensional holes. in your space. And so let's look at an example because it's definitely worth doing. Let's take our group to be the integers. So G equals Z. And let's take T to be the unit circle, or complex numbers of modulus 1. So this is just the circle. And clearly, the fundamental group of the circle is the integers, and all the other ones disappear. So T is a classifying space. T is a classifying space. It's not they're unique up to homotopy, but they're not unique up to homeomorphism. There's different models that are useful. And so we're able to read off the homology of Z. This is Z if n equals 1 and 0 otherwise. Okay. Let's see. I will say there's another definition, I guess, of homology that doesn't come from the classifying space. You could define this purely from functors and things like this, and it's actually a theorem that they agree. Okay, so let's write down some basic facts about these things and then look at some examples of homology groups of groups. So in general, maybe that's too light a color. HN is hard. It's hard to compute. Certainly past 1 and 2, it gets really difficult. But there's some nice cases for 1 and 2. First one is that the first homology group is just the abelianization. So this is the commutator subgroup. Just take G mod the commutator subgroup, and that's your first homology group. And the second
Sorry,
condition
what is
that
your notation for this commutator subgroup? I don't see.
DG.
D, yes?
Yeah, DG
DG.
for the derived group.
Ah, derived, okay.
Yeah.
So sometimes denoted by the square bracket, yes?
Yeah, but this is nicer. Well, it's easier to write 1,000 times.
Okay.
Yeah. So if H1 of G is free, so it's an abelian group, so free abelian, then we actually have a characterization of when H2 is 0. And I'll get to some examples in a second. This is kind of dry for now. H2 is 0 if and only if every central extension, so we'll write this as 1K SG, central meaning that K is in the center of S, if every central extension splits. Okay. And you might have some comments about cohomology, but the cohomology classifies central extensions so they're related, but they're not the same. They're related through a universal coefficient theorem, which for some of us, for me, it's kind of a weird thing because I think of the UCT in terms of KK theory and K theory for C-star algebras, but obviously it's inspired by these universal coefficient theorems from homology and topology and things like this. And this is one of them. So H2 cohomology is related to H2 homology via UCT.
Sorry, I have a comment/question. Probably the
Sure.
same is true for Hochschild cohomology. of algebras, but maybe there are some details. I don't know.
Yeah, I don't know too much about Hochschild cohomology. But this H2 with the superscript has a coefficient space, which will be an abelian group, and it classifies the extensions of your group by that abelian group. But we're not going to be interested in cohomology, so just a mark about that. And oh, I got my Zoom thing. So I'm just going to give a brief, maybe motivation, I guess, why central extensions are important. There's a recent paper by Dedarlat and Forrest Glebe related to almost representations. And they use central extensions to talk about almost representations of certain groups. We're not going to talk too much about central extensions. I mean, at the end with the universal covering group, sure, but just trying to motivate why they're important. This Kahn's invariant chi, so chi of m for a 2-1 factor or just a factor. This is some central extension of some quotient of the approximate inners. And so chi measures, notoriously whether or not an algebra, a von Neumann algebra, is isomorphic to its opposite. And so these central extensions play kind of a role with symmetries in algebras. And also algebraic K-theory. K2 alg.
Sorry, could you repeat what this chi is?
Sure. So this chi is just some, really it's the center of the approximate inners mod your inners for a 2-1 factor. And it's this group that Kahn's used to come up with factors which weren't isomorphic to their opposites. And it comes as the K term in a central extension. And that's it. Yeah. I don't want to get too much into it because it's quite a difficult thing.
Thanks.
But it is an interesting invariant. And it comes from these central extensions.
But sorry,
Okay.
it is directly related to algebraic K2 or just indirectly?
Algebraic K2 it is a second homology group. So it actually is the K term. That's why I use the K term there. So this is a central extension by the derived group of these invertible matrices over your group A. Or
Yes,
your
but I'm asking about the center of this inner automorphisms. Is it somehow related to algebraic K2? Only the common theme is this notion of central extension, yes, but there is direct connection between
No.
Okay, I see.
Not that I know of. I'd like there to be, but not that I know of. Okay. So let's lay down some definitions. I'll be interested in 3 types of groups. G is perfect if and only if its first homology group vanishes. It's super perfect if both the first and second vanish, and it's called acyclic. So maybe people have seen this term before. If every homology group vanishes. And so we'll see examples of all these. But let's do some basic examples. So first off, DG is a normal subgroup, right? So simple groups are perfect. So take your favorite simple group, its first homology group vanishes, And we've already seen an example, namely the integers, where the first homology group doesn't vanish. So for example, you could take A5, the alternating group.
Yeah. Mhm.
But the interesting thing about A5 is actually H2 of A5 is Z2, the cyclic group on of order 2. And now I'll be honest, I'm not a finite group guy. So I looked this up on Wikipedia, and apparently the central extension, which gives us this, it's called the, I'll just write this group like this. So this is a central extension, and this is called the binary icosahedral. Let's write this neater. Icosahedral group. Its order is 120. So this gives us some central extension of A5, and so H2 can't be 0. And actually this Z2 group, this central extension, this is exactly this. But I'm not sure where this group comes from. It's a geometric thing for sure. Apparently this group also is the first, aka smallest, super perfect group.
Sorry, so I have a question. So you said that the
Sure.
so the H2, the cohomology classifies extensions, and
Yes,
and here, oh, it cannot be 0 because you have a central extension, but we don't know if.
exactly. So it turns out that there's something called the universal central extension as well. And the reason you get the Z2 term equals this H2 group is if you have a universal central extension, then the kernel in that central extension is actually your H2 group. So this is universal. So it's that there's something extra nice about this central extension that's going on. But yeah.
Okay, thank you.
Okay, so these are groups that I don't know too much about. So let's start to get into things that I do know about. So groups coming from operator algebras. There's some other groups before that, which I'll just briefly say out loud. There's these Lie groups that if you take non-trivial connected Lie groups, actually their H2 groups will always be non-trivial. And this is a result of Saw and Wagoner. I won't write that, but so it's kind of not that common to have your H2 be 0 is the point, I guess. But in the context of operator algebras, we have many groups, many automorphism groups. And I won't actually have automorphism groups, but I'll have automorphism groups of spaces, not of operator algebras. So spaces are acyclic. And this is a theorem from Delaharpe and McDuff. So the following are acyclic. So if you take the symmetric set on infinitely many elements, this will be our acyclic. We could take automorphisms. Where's my of
So
a
once again,
Wigner
what
vector
is
space.
sigma of X?
This is the symmetric set or symmetric group.
All permutations?
Yeah, the permutation group with X infinite.
Okay, but now this group is uncountable,
Yeah,
provided
yeah,
you consider all possible permutations. So-
sure, but that's fine. We're not saying anything about the cardinality of the group. We don't really care.
Okay.
We just care that the homology groups vanish, right? Actually, all the groups I'm going to write down are uncountable. And the end goal is to look at unitary groups of C-star algebras, and these are always uncountable as well. So I'm not interested in cardinality of my groups.
Yes, but I have a problem since this symmetric group is something which is very much discrete, but uncountable.
Yeah.
But unlikely the unitary group and so on. So you always want your groups to be discrete, even for
Yes, I'll always want them discrete, even when I have a nice topology or several.
Mhm.
I will always look at the homology as a discrete group.
I see.
Yeah.
So in some sense, those are huge objects, yes?
Yeah, that's the point. Acyclicity is kind of this property of big groups. Big groups should be acyclic. Is a good idea for it.
Mhm.
Um,
Okay, thank you.
so there's measure preserving automorphisms of a Lebesgue space with mu infinite, so it's not finite, and non-atomic. So we get kind of automorphisms coming from measure theory, which would kind of tell us that, you know, things in certain von Neumann algebras, at least in the infinite setting, should be acyclic as well. And this is true. So if you look at GLH or the unitary group of H for H a Hilbert space, these are acyclic. Well, the following are acyclic. These ones are acyclic. And also, if we look at GLM or U of M for M, a properly infinite von Neumann algebra, this is also acyclic. But yeah, I mean, if there's a
Ali, have
question,
a
go for it.
question, Ali?
Yes, I have a question. Inspired by the question of atoms, I wonder if there's symmetric. There is a countable subgroup of the symmetric group, the all permutation with a finite support. My question is that is this reduced version of the symmetric group is a cyclic group or no?
That one I have no idea. I'm not sure. I wish I could tell you. Yeah, I'm not too sure.
Yes.
Yes, I have a question. Is there some obvious reason why automorphisms of probabilistic spaces are not acyclic?
Automorphisms of, sorry, what?
Probabilistic spaces. Because you assume that the measure is infinite.
Yeah, so
assume that
a lot of what's going on here, a lot of what's going on here is, at least with well, okay, I mean, I'm not sure, but here's another group that's acyclic. It's the which is finite, but I don't know if it's finite. I don't know if it is in the measure sense, but there's continuous functions on 0, 1. And if you look at the homeomorphisms of this is acyclic. I forgot to write this example, but I think this is due to math error. And I don't know about the
Sorry,
measure
what do you mean by
version.
homeomorphism? You mean automorphisms?
Yeah. Well, automorphisms of continue.
Okay.
Well, yeah. Sorry, homeo 0, 1.
Yeah. Yeah.
Yeah. And also homeo of R is acyclic. But yeah, I don't know about the measure version.
Mhm.
Yeah. Any other questions?
You mentioned some connection between simplicity and being acyclic. Could you remind me?
So if you're simple, you are perfect because your H1 is your abelianization, which has to be trivial if you're simple. But it doesn't say anything about acyclicity.
Okay, so only
Uh,
H1, or it only controls H1.
Yeah. So for example, A5 is a simple group that has non-trivial H2.
Since
Yeah.
as I remember, this space homeo of 0, 1 is simple.
Okay.
As far as I remember, I'm not
But it's
100% sure, but probably it is.
I'm not sure, but it is acyclic. It's a rather large space.
Yeah.
But yeah, there's this result of Mather. I think it's Mather. I didn't write this one down. But yeah, anyway, I guess for me, questions pop up, what about GLA, U of A for invertibles or unitaries in the C-star algebra, and also GLM, UM. So this is the von Neumann analog of that question that was just asked for a 2-1 factor. And this is a C-star algebra.
And do you expect the same answer for any possible 2-1 factors? Since there are plenty of them. There's only one
Well,
but all of them is the space is very rich. So
yeah, I have no idea. It's still open. It's still open.
yeah, but maybe some intuition. Maybe you have some intuition about it.
Well, I'm not too sure. I tried pretty hard at some point, but what I can say is it was kind of proposed like a Dilharb and McDuff proposed a kind of the reason I'm talking about universal covering groups is they mention if your universal covering group of the unitary group of a 2-1 factor is perfect, then you actually get non-trivial H2. And I answered that question, which we'll see at the end. But it leaves open this H2 question. So it's still unknown, yeah.
Tomek?
I have a question about the GL you wrote.
Yeah.
Twice. What do you mean by GL of A?
So the invertibles.
Invertibles. Okay.
Yes.
GL1.
Yeah, GL1.
Okay.
Yeah.
Thank you.
And oftentimes, at least for the C-star algebra setting, to answer this question, I'm gonna put knots here. So for example, U naught equals connected component of the identity in A, in the unitary group. And that kind of helps a lot. Well, yeah. Any questions so far? I'm going to move on to determinants to kind of answer some of these questions, at least for the C-star algebra case.
Yeah, sorry, actually, I have a question because you said you don't care about topology, and now you're talking about connected component.
Yes. I will think of U naught of A as a discrete group. And at some point, we're looking at U of M. And to construct this universal covering group, I need to use topology on M. I'm going to use the norm topology. And then I'm going to forget about the topology. It's a very like back and forth thing between topology and discrete. But when I'm looking at homology groups, I'm always interested in these groups as discrete groups.
So first you view GL of A as a topological group with its natural topology, then you take connected component, and now you are asking about the homology groups, and then you treat it like a discrete group, yes? Once the
Exactly.
connected component is already taken, yes?
Yeah.
Okay.
Yeah. So
Makes sense.
In some cases, you don't have to do this. So for example, these von Neumann algebras have the connected component is everything. So you're just looking at them as discrete groups. But in a lot of cases, it really helps for my purposes to look at the connected components. Maybe it's a bit restrictive, but anyway. Okay, let's start talking about determinants. So this is section 2, determinants. So we'll see examples of some groups that are not acyclic. That's kind of the point of this. So determinants on C-star algebras. Well, the determinant on Mn just gives you a complex number, but we can restrict it to GLN, and this gives us a non-zero complex number, or we can restrict it to the unitaries, and we get a modulus 1 complex number. But the point is, these are just group homomorphisms to abelian groups. Right? And you can think about what the kernels of these maps are, and then think about H1 groups, because we're always going to have this derived group sitting in there, right? Back equal. And so these determinants on the matrix algebras at least allow us to determine the first homology group. And I want to do the same thing for general C-star algebras. And then this was introduced to study algebraic K1 groups of C-star algebras, which is an H1 group. It's just you have to stabilize your invertibles and unitaries, etc. But okay, so how do we define determinants on C-star algebras? Well, we've got this equation where the determinant of an exponential is e to the trace of that exponential. And so we want to use traces. So I'm going to be a bit weird by what I mean by a trace, but that's okay. Hopefully it's clear. My traces are always going to be restrictions of actual traces. So let A be a unital C-star algebra. I'm sorry if you hear people yelling. I guess it's a noisy hallway. So we're going to take a unital C-star algebra, and I'm going to take tau from A self-adjoint elements into E. So this will be a real vector space. Well, okay. Let tau be a trace. So this just means tau of A star A is tau of A star for all A and A. Right? A star A is always self-adjoint, so it's always positive. Well, it's always positive, so it's self-adjoint. Right, and we want this to be an R linear map, which is tracial. And the reason I'm working with self-adjoints is because I want to talk about unitaries. And if I wanted to talk about invertibles, I would just take a trace from A to a complex vector space. And it's kind of nice when I do this generality because there's kind of universal vector spaces that come up. Like, I'll write it down in a second, but the affine or continuous real valued affine functions on the trace simplex is a nice universal vector space that we can get a tracial map to. So we have a trace. Let's look at examples.
Wait,
So-
Paweł, I just want to make sure we are on the same page. So you
Mhm.
now define a trace just by saying that everything is normal, right? A star, trace of A star A is trace of A star. So you
Yeah.
modify, right? And then you
Yeah.
take values not in numbers, but in a real vector space.
Exactly, yeah.
Okay, thank you.
And you'll see the motivation in a second, but if I take the restriction of a tracial state, so a state on a C-star algebra is a norm 1 positive linear functional, and obviously it's going to send the self-adjoints to self-adjoints. So tau will go from ASA to R. Okay, and this second one is why I like to include this vector space, because you can take this universal trace from A, and what we could do is we could take this space of things that vanishes on every trace. It's the closure of the commutators, and take the quotient map, and this will be a tracial map by definition. But yeah, is there a question?
Yeah, go ahead, Tomek.
Yes, I have a question about the extension of your
Yeah.
real trace to a
Yeah.
trace on A.
Yeah.
What is the abstraction?
I'm not really interested in extensions. I'm more interested in restrictions. Of course, you could extend things. Will it always be, you know, a nice tracial state, for example? You know, you could take the complexification and then do it like that. But I'm not interested in complexifying. I'm interested in starting with like something nice, like a tracial state, or this universal trace, and then just restricting to the alpha joints. And the only reason I'm doing this is because I want to work with unitaries instead of invertibles.
Okay.
But yeah, it's just a matter of me being a bit maybe silly. Maybe I shouldn't have restricted myself to real traces, but I prefer to do it this way. And the reason I prefer to do it this way is we could take this universal trace. So if we take the restriction, I'm still going to call it the same thing. From the self-adjoints to the self-adjoints, I'm going to call this set A naught. This is now the set of things A and A, where tau is the wrong thing to use. Sigma of A equals 0 for all sigma, a tracial state. So in the trace simplex. I'm going to write this better. So this is all self-adjoints such that sigma of A is 0 for all A or sigma in the trace simplex. So this is the simplex of all tracial states on A. And this restriction is interesting because this thing on the right can canonically be identified with the affine real valued functions on the trace simplex, which is a nice vector space, right? And this is why I wanted to generalize, well, A restrict to self-adjoint things for the unitaries, be generalized to vector spaces so that I can include this universal trace as a trace. And another thing is the center valued trace on a finite von Neumann algebra.
I have a question.
Yeah.
If you embed self-adjoint elements into A,
Yes.
then probably you obtain a commutative diagram, like composed with these two arrows and some others. But what about the intersection of the closure of the commutator with self-adjoint elements? Can you
So this is
compare
actually this
A0
space
with
A
this?
naught.
It is exactly
it's actually,
A0.
Yeah. So
Thank you
A
very
naught can be considered, you can actually write this explicitly. I think it's
Okay.
Pedersen and I forget the other name. Forgive me for that, but the A naught is actually the closure of the span of the self commutators. And it's also the intersection of the things that vanish on every trace with the self adjoints, right? Because this closure of the commutators is exactly the set of all elements that vanish on every trace. Tracial state,
Okay.
sorry.
Thank you.
Yeah,
I
but there is a relationship.
Yes, thank you.
And the point is that this thing ASA, this embeds isometrically into this other one. And this is why we can take this restriction quite naturally. Okay. Let's see how we're doing. Okay. Cool. So to a trace now, we're going to associate two things. We should keep these examples in mind. They're really the only thing that matter. Actually, 2 and 3 are the only thing that matter for this talk is the universal trace, because that allows us to look at first homology groups, really allows us to look at algebraic K1 groups. but we're kind of not stabilizing, and algebraic K1 is kind of a stabilized version of this first homology group. And this third one is what we're going to use to talk about these universal covering groups at the end. Okay. So one can associate a predeterminant so defined on, let's call this PU not of A. So there's a reason I wanted these connecting components, and it's because I like these determinants. And this is going to be the continuous functions to U naught of A, which start at 1. So I'm going to write this definition down and don't think about it too hard because, so let's do a tau here. It's kind of, there's a lot of work that goes into this definition. So now I'm showing an eta. So if I take a path, continuous function from 0, 1 to my connected component, I can actually find another path, eta, which is homotopic to Xi. Eta is piecewise smooth. And has the same endpoints. And once I have a piecewise smooth path, I can actually take its derivative and then I can plug it into this expression I have here. You take the trace, you throw a 1 over 2 pi I somewhere, take the derivative, and you multiply by the inverse. And you know, it could take a while to explain where this comes from, but if you think about MN, for example, I won't go into it, but this is well defined. So let's think about the path Xi of t equals e to the 2 pi I t a in MN, if you like, and throw that in there. And you just recover the trace of A. And this map is homotopy invariant and all these things. It's well defined, but this is the work of De La Harpe and Scandalis. This is well defined. It's homotopy invariant with fixed endpoints. And it's actually a group homomorphism. Okay, this is I'm calling the predeterminant. It's kind of bizarre, but it allows us to define an actual determinant. Okay. Let's say the determinant associated to tau. So this will be a map delta from the connecting component to our space E, our vector space. And what we're going to do is we're going to mod out by this predeterminant on the fundamental group of U of A. Right, if I've got a loop, let's just mod out by that. And again, this is so this will take U to, well, the class of the predeterminant of Xi, where Xi of 1 equals U, is any continuous path with endpoint U. And this might seem really bizarre, but again, just think about this path e to the 2 pi ita, and it kind of clicks, but there's a bunch of properties that make it work. And again, it's a theorem. This is a well-defined group homomorphism. And this is to de L'Arbin-Scandalis. So I'll go through an example in a second. But some properties of this group homomorphism. First off, it goes to an abelian group, right? E is a group with vector space addition, and we're modding up by some subspace, still group. So because we're going to an abelian group, we get that the derived subgroup is contained in the kernel, right? And there's another property where if you just look at an exponential, this is just the class of tau of A. Right, this follows directly from what I wrote above. Think about this path, the predeterminant applied to the loop, not the loop, the path e to the 2 pi ita will give me the trace of A. So far, so good. And I will say this determinant is related to other determinants.
So, sorry, can I have a question? Can you show your formula for this
Sure, yeah.
determinant again?
This predeterminant thing, right?
Yes, and then what is tau in this?
It's our trace. So we have a C-star algebra with our trace.
Okay.
So we have A tau. So tau is a trace going from the self-adjoints to some real vector space. And this integral, I will say, is the Riemann integral in E. So if E is, say you have a tracial state, all you're doing is integrating in the complex numbers. Well, actually the real numbers, if we insist E is a real vector space. Okay, I think it's worth looking at the example with the complex numbers, right? A equals C. Well, the determinant gets kind of boring. We have that the predeterminant of tau. Well, what's our traces? Well, let's take the identity function. This is just a map from the paths of our unitary group, so PT, to the real numbers. And all it does is it picks something here, takes a line segment, and then integrates it. And then our determinant is from the unitary group of the complex numbers. And it goes to R mod this fundamental group of our unitary group, which is the circle. So we just get the integers, and we just get T again. And actually, this determinant is an isomorphism. Okay. Cool. And yeah, this is related to the determinant on Mn. And there's also this Fuglid-Caddison determinant that this is related to. I won't write how, but so we have a determinant, and that's the point. And there's some remarks I want to make about this fundamental group. So one is that this fundamental group of the unitary group, it canonically gets sent to the fundamental group of this stabilized unitary group. By that I mean take unitary matrices at each level, take this inductive limit, and then we're looking at unitary matrices over A, and let's restrict ourselves to the ones connected to the identity, although because we're looking at the fundamental group, Doesn't matter if we're connected to the identity. There's this result, more or less Bott periodicity. The fundamental group of this stabilized unitary group is just the K-naught group. And this map is often surjective. So really our determinant is looking at our unitary group, the connecting component, and going to some vector space mod K-naught. And we have this commuting diagram, U infinity naught of A. With these predeterminants, there's some kind of stabilized predeterminant as well, and it's defined the same way. And this diagram commutes.
And,
So
and
actually,
this,
if
Paweł, and this horizontal arrow in your diagram, that's just induced, right, from a morphism you have
yeah,
groups. Okay.
it's just canonical. So
Canonical.
this is an inductive limit. So let me write this here. This is an inductive limit of the unitary groups of A. And with the connecting maps, just taking a unitary U and adding 1 in the bottom right-hand corner. And so we're taking all the unitary matrices in matrix algebras over A. And I mean, this is how one studies K-theory classically, right? You look at these either projections in matrix algebras or unitaries in matrix algebras. And there's nothing really new here. I'm just trying to restrict myself. Okay. So this is often surjective. So I'll give 2 conditions. So e.g. Z stable or stable rank 1. So for example, classifiable C-star algebras in terms of the Elliott classification program, these all satisfy the surjectivity condition. In fact, it's a isomorphism in that case. And stable rank 1, so for example, the continuous functions on the unit circle, you get this surjective map with K-naught. And the point is, because of this, so this, if we take trace of A, the universal trace, and we're looking at affine functions on trace simplex, I'm going to write rho A of K-naught of A, and rho A is the pairing map. So this will agree. So again, this is a bit of a technical thing, but if you look at the predeterminant on a loop of this form, e to the IP for P of projection, you actually just get the trace of that projection. And this pairing map just takes a projection to the function, which just applies the trace to it. And so this pairing map between K-theory and traces is just our predeterminant. And of course, I don't want to get into K-theory, but K-theory is classically pretty computable. Like you could just write down K-theory groups, and that's going to be useful for examples of things which may or may not have vanishing homologies. Okay, so we get this often. Okay, so far so good. There's also the question of what's the kernel? Well, again, often, this is to Ing and Robert, the kernel is actually the commutator sub. And I'm writing often because I don't want to get into all these technical conditions, but often includes classifiable C-star algebras in terms of Elliott. So unital, simple, nuclear, Z stable, separable, satisfying the UCT. C-star algebras, like the reduced free group C-star algebras, these satisfy this condition. And I will say it was known that C-star F infinity did, and recently there's this paper by Tetwamasi Armatan, Shri, David Gao. I'm not saying Shri's last names because I forget them, and they're hard to say for me. So Shri and Greg Patchell, and they showed that these reduced free groups have strict comparison, which implies this result. They fall into this theorem of Ing and Robert. And so the kernel is always nice. Well, sorry, not always, often nice. For all the C-star algebras people care about, the kernel of this determinant map is nice. So what's a corollary? Well, the H1 of U of A, which is the abelianization, well, it's going to be the affine functions on the trace simplex minus, or mod, sorry, the K-naught group for nice C-star algebras. So classifiables, for example, or free group C-star, reduced group C-star algebras. And what do we get for free? Well, we note that, you know, app T of A, this is a real vector space. So it's uncountable. Okay. K naught of A is countable if A is separable. Right? So when we look at this group, whenever we have traces and your C-star algebra is nice, and you're separable, you can't banish, your first homology group can't vanish. Okay. So really these von Neumann algebras are kind of nice because they're nice and non-separable, or the, you know, the infinite ones don't have traces. You could actually say something. So for infinite, purely infinite, so simple, you actually get H1 of U of A is 0. But so the obstruction seems to be traces is the point. And separability. Together they give us a pretty big obstruction. And so again, this question from the beginning, what about 2-1 factors? They have traces and they're non-separable. And actually it is true that the commutator subgroup is everything. So Breuson, Factila, Harp, U of M is actually du of M. And again, these are von Neumann algebras, so I'm not putting the connected component. So this implies H1 of U of M equals 0. I don't know why I'm putting a question mark. Okay, so far so good. So it's been purely expository so far. So let's throw in some results, I guess. Let's take a detour into GL, and then we'll talk about covering groups. Well, there's a theorem I have with Aaron Quetius, and George Eliot did something similar, although I'm not too sure if he did the unstable case. But it says for, I'm going to write often again, for very nice C-star algebras, the same ones that satisfy this condition of Ing and Robert where the kernel of the determinant map is nice, you get that the H1 of GL, let's put the connected component, although we don't need it in this case, actually. So I'll put that in red. GL of A is naturally isomorphic to the H1 group, the unitary group, plus traces. Okay. And we could put the connecting components if we want. So a corollary is, again, we don't get perfectness. So we can't have acyclicity if A is tracial. And this is actually still true for von Neumann algebras, or even the 2-1 factor case. Like the unitary group for the 2-1 factor case is kind of, you get trivial first homology, but you don't get trivial first homology for the invertibles. Okay. For 2-1 factors. Well, von Neumann algebras. Okay. Hopefully that's okay for examples of unitary groups and then whether or not they're perfect. So now I want to talk about these universal covering groups. So Pierre de la Harpe and Duce and McDuff, they kind of proposed this problem, which is actually, it doesn't quite come from them. It's around in the literature of if you have a nice topological group and you want to look at its second homology group, well, why not look at the universal cover? But look at the universal cover of U of M. So this fits into some central extension. So I'll say what the universal cover is. So let's look at the universal cover. And for homological reasons, if this is perfect, this implies H2 of U of M surjects onto pi1 of U of M. And this is actually just the K theory of M, which is the real numbers. So they kind of proposed looking at this universal cover group. But it's kind of a big if. So what I'm about to write down, it's not true that this is perfect. You can actually explicitly compute the universal cover. And that's what I'll get into next. So big if. So what's the universal cover? Maybe for time's sake, I guess, I won't get into the exact definition because it could be quite bland. I'll say it out loud, but I'll just do an example, which is the standard example. So the circle, okay, I'll say that it's a space with a surjective homomorphism. Let's say of G, of a topological group G now. Also, I will say, this fundamental group thing, this is with the norm topology. Obviously, this is a 2-1 factor. It has lots of topologies, the SOT topology, the 2-norm topology, which agree on bound sets, and the norm topology. And actually, U of M is contractible for the SOT topology. So there is no fundamental group. We're looking at the norm topology. To somehow forget it to talk about the discrete homology, it's a bit silly, but it's important that we consider the norm topology on our 2-1 factor. So the universal cover of a topological group, well, a cover of a space X is some space with a surjection, a continuous surjection. And it satisfies some properties. So I'll just do an example. If I want my space to be the unit circle, what I could do is I could take the real line R, and I could kind of think of it as this helix thing. And then I could map it onto the circle, right? Let's call this rho. I could take rho of t to be e to the 2 pi I t. And a cover is a space such that locally we could pull things back, kind of in a discrete way. So this just means for every point in my space, if I look at the pullback under this surjection, so let's pick a point and let's pick a neighborhood. I could actually find disjoint neighborhoods, each of which are homeomorphic to my neighborhood. And this is the classic example of a cover. Okay. So each point has a pullback, has a neighborhood, which gets pulled back to disjoint copies, each homeomorphic to the neighborhood under the map. So this is what it means to be a cover. And so a cover is universal if it's simply connected. So this means it has trivial fundamental group. So let's write this better. And so this guy is universal because R obviously has trivial fundamental group. Okay. And we'll say the universal cover group of a topological group. Of course, we were talking about discrete groups before. Now let's talk about topological groups. Topological group G is a universal cover G tilde, which is a group. And this map, this surjection, is a hom. Okay. So for example, this covering of R over T, that this is a universal covering group of the circle. Okay. And some remarks, I guess. These don't always exist. But when they do, you can write them explicitly. So PG, G tilde will be homeomorphic and algebraically isomorphic to this PG mod sum equivalence. So remember, PG was this space of paths, the continuous functions to our group, which start at the identity. And this has the compact open topology, if you want it to be a homomorphism. So it's not the uniform topology on C01 to G, the compact open topology. And this equivalence relation just means two things are homotopic with the same endpoints. So C of 1 equals 8 of 1. And okay. So they don't always exist, but when they do, we can write them down. And so here's a nice little lemma. The universal covering group of any C-star algebra, of any unitary group, the connected component always exists. In particular for 2-1 factors this time. Okay.
So here it's really any C-star algebra.
Any C-star algebra. I'll be interested in the 2-1 von Neumann algebras, but any C-star algebra. And the reasons are so things exist, covers exist if there's three conditions. You have to be path connected, locally path connected, and locally or semi-locally. The name for this kind of varies. Semi-locally simply connected. So I'll just draw a picture real quick. If I take, for example, the annulus, the first thing path connected is obvious. Local path connectedness just says, okay, I have a point and I take any neighborhood. I could find a sub-neighborhood which is connected. Okay, I could do that. The other thing, so this is locally. The other thing is this semi-locally simply connected. Just says for every point and any neighborhood around that point. So again, let's just do something like this. I can find a sub-neighborhood which is contractible, which I could do, no problem. And it turns out that you could do this for these connected components of unitary groups. Obviously, they're path connected by definition. You're looking at a connected component. Local path connected takes like a line of work, and the simply connected also takes like a line of work. These exist. Yeah, question.
I think the last condition has a modified definition. If I'm not mistaken, the last condition means that for every big neighborhood, there exists a smaller neighborhood such that all loop in the small
Exactly.
neighborhood can be retracted to a point in the bigger neighborhood. This doesn't necessarily implies that the small neighborhood is contractible. If I'm not mistaken,
you're right. Yeah, I just mean that basically you have a neighborhood whose fundamental group is trivial.
Yes, but this doesn't mean that the red neighborhood that you are drawing is contractible.
It's not contractible.
Yes.
Yeah.
No. It's not the problem of contractibility or fundamental or pi1 is equal to 0. I mean that I think the true definition is the following: for every big neighborhood, there exists a smaller neighborhood as the red one that you draw. That all loop in the red neighborhood can be shrink to a point, but not in the red neighborhood, in the bigger neighborhood. I mean that the inclusion of the small neighborhood to the bigger one is induced a trivial map in the fundamental group. I'm not sure, but I think that this is the true definition.
But sorry, Ali,
Okay, in either case,
what you have explained is probably locally simply connected without the semi-locally. That would be
Yes.
my guess.
Yes. This is the justification for what I say. We are not we are not saying locally simply connected. We say semi-locally simply connected.
yeah.
Yes. But probably the condition which you have described, I would say that this should be called locally simply connected. This described by you, not semi-locally. But
No.
okay, I may be mistaken.
In either
Uh,
case, I mean, C-star algebras are super nice. So we can do these things.
Yes. As
Okay.
another question, I wonder, you wrote that they don't always exist. So I wonder what is an example of a connected topological group for which there is no the universal covering space.
So like from what I remember, there's this thing called the Hawaiian ear ring. It just looks like this, and you go on forever.
The Hawaiian, yes.
Earring.
Yes. So this does.
Yes, but that's not a topological group. My question is that what
So
is
this is a space.
This
For a
is a
topological
space.
group, I don't know. Yeah. This is a
Yes,
space.
okay.
Yeah,
Okay.
I don't know about group. Well, I guess you could take something that's just not connected, right? That's silly though.
Yes, I see.
But
Okay, thank you.
yeah. All right. So anyway, these exist for unitary groups, so they exist for U of M.
Mhm.
And I guess I'll just state this theorem that I proved. I mean, I'll try to intermingle the rest of this, but before I do that, covers, universal covers, give extensions, which happen to be central from the fundamental group of G to the universal covering group to G. And this map here, if we're thinking of this as the paths modulo this equivalence relation, let's just evaluate at 1. And these give us essential extensions. Okay. So here's a theorem. M is a 2-1 von Neumann algebra, not a factor. Then this pi 1 of U of M, we go to the universal cover. We go to U of M. This splits algebraically. So again, I've done this thing where I've taken topological stuff and I'm just saying, let's forget about the topology. I just want an algebraic thing. So this splits algebraically as U of M. Okay. And the proof of this is really using these predeterminants I was talking about. Because you can show this sequence is left split by taking this predeterminant with the center valued trace. And that's more or less it. And so this question of Delaharpe McDuff is not true, right? Because this fundamental group is for a 2-1 von Neumann algebra is just the center self-adjoint parts of the center. So in particular for 2-1 factors, we have that this universal covering group is the direct product of R and the unitary group. But that direct summand of R just breaks perfectness. So the point is that these are not perfect. Obviously, it leaves open H2 of U of M still equals what? And something else that might be interesting is that I might plan on doing at some point, but is looking at universal coverings U of A tilde for A unital separable plus purely infinite. Because this will remove any trace condition. The separability and the trace condition will kind of remove any way I know how to split this sequence. And I would be interested in what kind of groups you can get. Would these be perfect? Things like that. But yeah, there's another question.
Tomek?
I think I'll stop here anyway. So
Tomek,
Sorry, it was not a question, maybe commented that the fundamental group of a group is always abelian. So
yes, yeah.
so this explains why in the center you have this pi1 of G, and
Yeah.
you are not asking about what is H1 of U of M, for instance.
No. But H1 of U of M is 0.
Yeah.
But H2 is still unclear. But at the very least, all this motivation about homology to talk about universal covering groups and then answer the universal covering group question in the negative, which still leaves the H2 question open. Nonetheless, I think it's an interesting result. And I still don't know how to do this H2 problem, although I've had thoughts here or there, but it never really worked out. So, but yeah, anyway, I'll stop here. Thanks for the attention.
thank you so much.
Thank you.
Okay, Ali, could you now elaborate what you wrote to me in chat?
Oh, let's see.
So could you? Yes, I wrote about the true definition of the semi-locally path connected. Are you talking about that?
Yeah. Because
Yeah.
send me some Wikipedia link. So now
Yes. I just share you. Yes. I just share you the link of the.
There's a horrible echo, Ali. What's going on?
Sorry.
There's an echo when you speak.
Well, nonetheless, these C-star algebras actually satisfy like this. I think they're actually locally simply connected, these connected components. But yeah, for existence of these universal covers, you want semi-locally simply connected. But you're right, there is a distinction.
So probably the crux of this definition is that this contractibility of this loop is realized in this whole space X, not necessarily in the chosen neighborhood. So,
Yeah.
You take a point, then you consider a neighborhood. In this neighborhood, you can find another smaller neighborhood that you taking every loop in this smaller neighborhood. It is contractible not in this smallest neighborhood, not in the original one, but in the whole space.
Yeah.
This way. Okay. So Ali, this is what you were writing?
I'm referring to this link on Wikipedia.
Okay, great. Yeah.
And this confronts, this is in accordance with what I've said, that this condition, as far as I understood Ali correctly, was about not semi-locally simply connected, but locally simply connected. So locally simply connected would mean that you start with one neighborhood, then you can find a smaller neighborhood, that every loop in the smaller neighborhood is contractible not in the smallest neighborhood, but in this original one, but not in the whole space. So
Yeah.
this condition would be stronger.
Yeah.
Mm.
So this is without semi.
Without semi, yeah.
Okay, and this is stronger.
Mm.
Okay, Ali is nodding. Now, Tomek?
No, I'm fine.
I have a question, but very
Go ahead, Adam.
vague and very general and vague. Do you expect some relation between your the topics which you have covered with the quantum field theory? Since in quantum field theory, people are, first of all, very often interested in central extensions. There are also in string theory, there are diffeomorphism groups. And also probably this type 2 algebras also appear in this context, but on the other hand, in quantum field theory, type 3 also appears very frequently.
Yeah.
Which is
I'm not too sure.
properly.
Yeah. I'm not too sure. I'm. I don't know. I don't know too much about quantum field theory. So. But if type 3s appear, I mean, everything, these are just properly infinite von Neumann algebras. So everything kind of like everything we've talked about trivializes in this setting.
For type 3, yeah.
Yeah.
But okay, we also had some talk on this seminar about a possible connection between the tentative, so some sort of proposal for a theory of quantum gravity and 2-1 factors. This hyperfinite 2-1 factor. So probably also this 2-1 business also enters in this consideration related somehow to physics.
Okay, good to know. Good to know.
Whose talk do you have in mind, Adam?
Sorry?
Whose talk do you have in mind?
Okay. I don't remember the name, forgive me, but it was the talk after which was a lengthy discussion. This was on site in Warsaw.
That's what typically happens. So you couldn't.
But very lengthy. Probably it was a.
I know that was this guy from Budapest. Yes.
Yeah, exactly.
Okay, yeah, no. Okay, Tomek.
Yes, I have a question about generalizing this formula for this homomorphism given by the integral of the trace of something like non-commutative logarithmic derivative.
Yeah.
Okay. So can you extend this homomorphism to something using some cyclic cocycles instead of traces?
Yeah, so I think this sort of thing has come up in that context, but I don't know too much. But I think this has come up in like cyclic homology and the same kind of idea, actually using traces. And you get some sort of, but I don't know too much about the topic, but I know I've seen related things there. Maybe that's a bit disappointing, but yeah, I don't have any detailed answer for that.
Okay.
Can you explain what's the result of this construction of delta tilde if you are on a finite dimensional Lie group?
Finite dimensional Lie group.
Yes. You can have paths on let's say connected Lie group.
I'm not too sure. I guess you would have a trace to the Lie algebra.
Yes.
I guess you could do the same thing, but I don't know what it would be.
But this construction should be known. If this makes sense for Lie group, it should be well understood in the classical setting.
Yeah, I'm not too sure. But certainly it seems like you could just, you've got a Lie algebra sitting around. As long as it's a Banach Lie algebra, you could do the Riemann integration.
So instead of a trace, you can take some linear functional vanishing on commutators, let's say.
Yeah.
Of a Lie algebra, yeah.
That might work.
I would like to understand if this is some infinite dimensional phenomenon of big groups, or is it some generalization of something which is well known for Lie groups, for instance?
Oh, do you mean the determinant or this
This kind of
this
determinant, of course, it depends on choices.
Yeah, so I think so this one was introduced by Diller-Harp and Skandalis, but actually these kind of techniques, I think they were used around the 60s when people were looking at homotopy groups of von Neumann algebras, of the unitary groups of von Neumann algebras. This kind of like thing where I say take a piecewise smooth path. Actually, you could always take exponential paths. And also there's the Fuglid-Caddison determinant that has a similar form. So I usually stick to Diller-Harp Skandalis stuff, but there was stuff beforehand, and I'm not sure where they got their motivation from. Maybe it was from Lie groups.
Okay, so I wanted to know how far back you can
Yeah.
go with
But
this.
I've at least seen this paper by I think it was a paper with maybe it was Smith and someone and from the 60s I think, where they used similar techniques, but I'm not sure where they got their motivation from. So it's quite an old thing.
I suspect.
Yeah.
Okay, thank you.
Just hasn't been used in the context of C-star algebras till the 80s, and then kind of reinvigorated with the classification program.
Okay, Tomek, are you happy now?
Yes, thank you.
Anybody else from the Zoom? I don't see any raised hands. Anybody from the room? Andre, you have some?
I said that it could be a matrix trace taken from fundamental representation or any other and only algebra.
Yeah. Yeah, I mean the finite dimensional stuff is the same, right? You would just take your
Yeah.
honest trace.
Yeah.
But it'd be interesting for Bernoulli algebras where you can actually integrate. And I don't know too much about infinite dimensional algebras, so.
Yes, so I have a kind of a general question. Maybe I missed it during the intro to your talk, but what's your original motivation to compute this H2 of U of M?
Well, I got interested in, so that it never worked out, but I got interested in homology groups of automorphism groups, like genuine automorphism groups of C-star algebras. And you try a bunch of things and they don't work, but you learn so much along the way, and I don't know, I kind of just liked this stuff. Obviously I'm still trying to do some of these things. I'd like to compute homology groups of these automorphism groups, like approximate inners and things like this. I think it'd be interesting because they're quite large groups generally, and I think they would fit into the for general C-star algebras. I don't think they'd fit into the framework for acyclic stuff, but like for C-star algebras that have basically no K-theory, like O2 or big C-star algebras, I feel like you could get something, and I tried, and but I learned a lot along the way, and then I got interested in these covers, but yeah, that's the motivation, just automorphism groups, I guess.
Okay, thank you.
Okay, so Tomek, what? You are muted.
Maybe question or maybe a comment about the last what you said about this motivation. So classically, if you consider homology of automorphisms of something, this problem is related to the problem of forms, a very classical problem from classical geometry, for instance. so in the classification problems, sometimes you can recover something which is not what you expected, but finally it's twisted by something, and
Yeah.
this twisted thing is called a form, and sometimes it's related to this homology of automorphisms. So do you expect in this case some analog of the problem of forms?
I'm not sure, but I know, for example, in this Condon variant chi, so this was in terms of automorphisms for this for factors. This came from some central extension, And so I think 3 homology classes come up with chi a lot, and maybe this is related to, sorry, 3 cohomology classes, and maybe this is related to these forms, but I don't know too much about the forms, so can't say much. But cohomology comes up for sure. And there are quadratic forms as well when it comes to things like chi. So I wouldn't be surprised if these things came up in general.
Okay, thank you.
Okay, so let's wind it up and thank our speaker again. Thank you so much, Paweł.
Thanks for having me, yeah. And I'll send you these notes.